Good morning to all of you. So in the last lecture, we were discussing about various definitions of AI, like on which basis the AI systems are defined. So there were four different ideologies, like thinking humanly, then thinking rationally, acting humanly, and acting rationally. Then we discussed that in acting humanly, what are the characteristics of human being are. So those characteristics must be mimicked by the AI-based agent. So for that, Alan Turing, which is also known as father of computer science, he proposed one test. In the test, these many capabilities are must-haves for a robot to work as acting humanly. Okay, so natural language processing, knowledge representation, automated reasoning, machine learning, computer vision, and robotics. All these capabilities must be there with an AI-based agent to perform just as a human being, act as a human being. So even today, this test is relevant. Then, in thinking humanly, earlier was acting humanly. In thinking humanly, the cognitive modeling approach is considered. Like when we see something, uh, whatever scene is there around us, that scene is interpreted by our brain. How the scene is converted into equivalent signal by eye. So from eye, there is an optic nerve which is connected to brain, so that optic nerve carries the signals about the scene around us, and that scene is interpreted in the brain. Okay, so this is one sensor. Second sensor is touch. So if we touch our hands or legs or some object or some surface, then how it feels, that information is again captured by our brain. Likewise, we have five senses, and once we gather the information from these senses, there is one faculty of brain, that is cognition. Cognition means to interpret, to understand, and to act accordingly. So action is a later part, but before that, to interpret, to understand, this is known as cognition. It is a interdisciplinary field of cognitive science that brings together computer models from AI and experimental techniques from psychology to construct precise and testable theories of human mind. Okay, so we don't know where the mind is. We know where the brain is. We know the physical location of brain, but we don't know where is human mind. So we have to combine the theories from psychology that are related with human mind, and the various computer models from AI. If we combine, we can construct a robot that can think humanly. Then next is thinking rationally. So laws of thought approach. There was one philosopher, great philosopher called Aristotle, and what he gave syllogisms. So all his syllogisms were based on the logic. In logic, there are only two things: either something is true or something is false. Here, one example is given. Socrates is a man. All men are mortal. So this is first sentence. Socrates is a man. This is true. All men are mortal. This is also true. Therefore, Socrates is mortal. So this is something which is concluded on the basis of truth, on the basis of logic. Okay. So his experiments are known as laws of thought. So based on these things, there is one language we are going to study, that is prologue, which is also based on logic. So only two things are there, true or false. So this is also one way of defining AI and constructing AI-based agents which are using rational thinking. Next is acting rationally. So what is rational thing? Rational means doing best under certain scenario. Doing best under certain scenario. Like there may be some ideal condition, but the ideal condition is not possible due to some constraint. Then the agent will perform the best under given constraints. Okay, so it may not be the best performance, but under those situations, it is somewhat good performance, we can say. So this kind of agent is known as rational agent. Say someone is driving a car. Suddenly a dog comes in front of the car. So it is not recommended to apply the urgent brakes quickly and take the car aside of a road. But in order to save that dog, someone took that, applied the brakes and took that car somewhat to the left side, which is not recommended. But this is the best thing the human can do under that scenario in order to save the life of that dog. So this is what under given constraint, the good thing or best thing is performed. So an agent is just something that acts. Agent comes from the Latin agere, to do. Of course, all computer programs do something, but computer agents are expected to do more, operate autonomously, perceive their environment, persist over a prolonged time period, adapt to change, and create and pursue goals. Okay. A rational agent is the one that acts so as to achieve the best outcome, or when there is uncertainty, the best expected outcome. So these are the characteristics of rational agent. Now here is one block diagram which involves agent and environment. Over here, we can see that this is environment, this is something that surrounds the agent. From this environment, the percepts will come. Percepts means inputs will come, and they come through the sensors. So you are the students of electronics, you know sensors and actuators. So sensors are something that can capture the processes around the agent, and actuators are something that can act into the environment. So that is something related with the action. So here the information regarding percepts or regarding the environment around agent, it is coming through sensor. It is given to this black box. Question mark means we don't know. And the actuators will perform the action into the environment. So why this is black box? Because what is to be done, that we are going to discuss that in the next few slides. That's why this question mark right now. Okay. So an agent is anything that can be viewed as perceiving its environment through sensors and acting upon that environment through actuators. Okay. So a human agent has eyes, ears, and other organs for sensors, and hand, leg, vocal tract, and so on for actuators. A robotic agent might have cameras, infrared range finders for sensors, and various motors for actuators. So cameras and IR range finders for sensors, and there are motors for actuators. A software agent receives keystrokes, file contents, and network packets as sensory inputs, and acts on the environment by displaying on the screen, writing files, sending network packets. Okay, so where is software agent? Somewhere over here. Over here, there is software agent. It may receive inputs from keystroke, file content, network packets, and it may act on the environment using some display like output, or it may write a log, so that log is written in file or sending network packets. We use the term percept to refer to the agent's perceptual inputs at any given instant. An agent percept sequence is the complete history of everything agent has ever perceived. So these terms are really important. Percept means agent's perceptual input at any given instant. So this is one input. 1% means at one instant, what is the input? Percept sequence means complete history of all the inputs that the agent has received. In general, an agent's choice of action at any given instant can depend on the entire percept sequence observed to date, but not on anything that has not perceived. Okay. So it may take decision on present percept or percept sequence, that is the present and past inputs. But if something is not shown to the agent, it cannot take decision based on that. By specifying the agent's choice of action for every possible percept sequence, we have said more or less anything there is to say about the agent. Mathematically speaking, we say that agent's behavior is described by the agent function that maps any given percept sequence to an action. So there is a percept function. This is the mapping. Okay. So like if x is the input and agent is doing sine of x, so sine is an agent function. And say x is the keystroke or file content. In file content there are values of x, and agent function is finding the sinusoid of that x, and the output is also file content in the form of log. Okay. So we can imagine tabulating the agent function that describes any given agent. For most agents, this word would be a large, very large table, infinite table. In fact, unless we place a bound on the length of percept sequences we want to consider. So like every time the agent perceives something, every time the agent views something, it is recorded as input and it is tabulated. Next time, if the agent perceives something, it is also tabulated. So this sequence length can be infinity, but we cannot have infinite GB data because there is a limit of hard disk and storage resources. So we have to put a bound, we have to put a limit on percept sequence. Given an agent to experiment with, we can in principle construct this table by trying out all possible percept sequences and recording which actions the agent does in response. So this is a mapping. This here to mapping, like this is the input, this is the output, this is the input, this is the output, like that. Internally, the agent function for an artificial agent will be implemented by an agent program. So there is actual software code. Agent program is software code. Agent function is theoretical meaning. Okay, it is important to keep these two ideas distinct. The agent function is an abstract mathematical description, like theoretical description about what the agent does, and agent program means it is a concrete implementation running within some. There is a difference between illustrated world figures. Over here there are two B, two squares are there, A and B. Okay, and this is a vacuum cleaner. What is the job of this vacuum cleaner? To clean that dirt. Has just two locations. Which square it is in and whether there is dust in the square. It can choose to move left, move right, suck up the dust, or do nothing. One very simple agent function is the following: if current square is dirty, then suck, otherwise move to the next square or other square. A partial tabulation of this agent is shown over here. If A is clean, move to right. If A is dirty, suck the dirt. B is clean, move to left. B is dirty, suck the dirt. Then A is clean, move to right, like that. Okay. So likewise, this percept sequence is recorded. Percept sequence is recorded, and these actions are also recorded in the form of table. Then rational agent, it is one that does the right thing. Conceptually speaking, every entry in the table for a function, agent function is filled out correctly. Obviously, doing the right thing is better than doing the wrong thing. But what does it mean to do the right thing? We answer this age-old question in an age-old way by considering the consequences of agent behavior. When an agent is plugged down in the environment, it generates a sequence of actions according to the percepts it receives. This sequence of actions causes the environment to go through sequence of states. If the sequence is desirable, then the agent has performed well. This notion of desirability is captured by a performance measure that evaluates any given sequence of environment states. So, ideally, the agent should perform some task that will be rated as 100 on 0 to 100 scale. So, that is something performance measure, that is 100. Under given constraints, achieving 100 is not possible because there are limitations, there are some real-time constraints which are put in this environment. So this agent, which is the rational agent, it performs in that particular environment, and it has got 90 as performance measure. Instead of 100, it got 90. So then also it is acceptable. But if the performance measure is poor, like 1, 2, 3, 5, 10, 20 out of 100, then it is not desirable. 90 is okay, it is desirable like that. All right. Consider, for example, the vacuum cleaner agent from the preceding section. We might propose to measure performance by amount of dirt cleaned up in a single 8-hour shift. So that is important. What is performance measure for vacuum cleaner? How much dirt is cleaned in 8-hour shift? With a rational agent, of course, what you ask for is what you get. A rational agent can maximize this performance measure by cleaning up the dirt, then dumping it on the floor, then cleaning it up again, and so on. A more suitable performance measure would reward the agent for having a clean floor. For example, 1 point could be rewarded for each clean square and at each time step, perhaps with a penalty for electricity consumed and noise generated. As a general rule, it is better to design performance measures according to what one actually wants in the environment rather than according to how one thinks the agent should behave. For each possible percept sequence, a rational agent should select an action that is expected to maximize its performance measure given the evidence provided by the percept sequence and whatever built-in knowledge the agent has. So here, for a vacuum cleaner, the how many squares were clean, there is one performance measure. How much dirt is cleaned up, that is another performance measure in an in 8-hour shift. Okay, so in 8 hours, how much is the performance? It is measured. Now, if the agent keeps on moving from left to right, if both squares are clean, and the agent keeps on moving from left to right, right to left, just to check, then what it will generate? It will generate noise, then it will consume the electricity. So this is not good. So it should wait for some time, even though say square A is clean, it should wait for some time and then go to square B. Then if there is dust, it should clean up the dust and wait for some time, then go to A rather than switching continuously. So this will optimize the performance. This will give the better performance measure. One can see easily that the same agent would be irrational under different circumstances. For example, once all the dirt is cleaned up, the agent will oscillate needlessly back and forth. Just now I told this thing. If the performance measure includes a penalty of 1 point for each movement left to right, the agent will fare poorly. Better agent for this case would do nothing once it is sure that all the squares are clean. If clean squares can become dirty again, agent should occasionally check and re-clean them if needed. If the geography of environment is unknown, the agent will need to explore it rather than stick to squares A and B. So this is a very simple problem. Square A and square B, and only two locations where the dirt is to be cleaned up. This is very simple scenario. But there are certain scenarios where the environment is totally unknown and continuously changing. Like the robot is made to move 5 kilometers straight. Okay, and the road is unknown. And whenever it finds some dirt, it should clean it up. So in this case, it cannot oscillate. It has to continuously update itself. So this is a different scenario. So in this case, the agent may perform irrational. Now, this important thing, specifying the task environments. So it is the description about where the agent works, okay, where the agent performs its actions. In our discussion of rationality of the simple vacuum cleaner agent, we had to specify the performance measure, environment, agents, actuators, and sensors. We group all these under the heading of task environment. For the acronymically minded, we call this the PEAS, performance, environment, actuators, and sensors description. In designing an agent, the first step must always be to specify the task environment as fully possible. Okay. So over here, just observe. This PES description for task environment for automated taxi. Okay, so the name of agent is taxi driver, automated taxi. So like driverless car. Then who is the driver? Machine is a driver. AI-based agent is a driver. Okay. So what is performance measure? What do you expect? There is no driver. Driverless taxi is there. So what do you expect? My ride should be safe, fast. It should be legal, comfortable trip. Maximize profit means this is for owner. Maximum profit should be gained. And then environment is roads. Then other cars, other traffic, pedestrian, then customers. Customer is sitting inside, but it is also part of environment. All right. So this is environment. So description environment. And actuators means something that will reflect the action in the field. So steering, accelerator, brake, signal, on display, all these are actuators. And sensors means something from which the information is gained. So what are these? Cameras, sonar, speedometer, GPS, odometer, accelerometer, engine sensors, keyboard. In addition to this, there is radar. Okay. So that also helps to get the information. So all these things are description about certain agent. So this PES description is really important. It was for autonomous taxi. Likewise, we have for medical diagnosis system, satellite image analysis system, part picking robot. Okay, so this is PES description. Then refinery controller, interactive English tutor. Now, there are some characteristics of these environments, task environments. Like if there is some crossword puzzle, okay, some crossword puzzle solving AI agent. Then for this, is the crossword puzzle fully observable? Yes, it is fully observable. How many players are there? Only one player, which is the agent. Whether the crossword puzzle is changing itself internally? No, it is constant, it is deterministic. It is not stochastic. Stochastic means something that changes, that is random. Deterministic means something that is constant. Then episodic, it is sequential or episodic. So it is sequential, one by one. It will go on solving the puzzle. It will go on fill up the characters. Then is it varying with respect to time? No, it is static. Is it discrete or continuous? So continuous means whether something is varying, like AI-based autonomous taxi driver. So there, the environment is changing continuously, right? Because the taxi moves. When it moves, the cameras will receive different input. The sensors will receive different input. So in that way, the environment is continuous. But here, in the case of crossword puzzle, it is discrete. It is not varying. So likewise, we can have the characteristic of task environment like this. Okay, so it is explained for other examples. Then, what is agent? What is agent? So we saw that in an agent, this is how the inputs come and it gives the output. So it has some architecture. It has some architecture, and it has some program. So that program will act according to the inputs it has received and the information that is stored previously. So based on the input and previously stored information, it will take the decision and it will give the signal to actuators to perform the action accordingly. So it is a computing device with physical sensors and actuators. So these sensors and actuators, they are part of agent. Then agent program is also a part of agent. So that's why it is called as architecture. Architecture means internal physical architecture which contains actuators and sensors and other parts of agent. Plus it contains the program which is executed based on the inputs. So likewise, we discussed the structure of agents over here. Just a minute. So the next part, the agent programs that we design this course all have the same skeleton. They take the current percept as input from the sensors and return an action to the actuators. Notice the difference between the agent program, which takes the current percept as input, and the agent function, which takes the entire percept history. Okay. So agent program takes current percept as input. Agent function takes entire percept history. Okay. The agent program takes just the current percept as input because nothing more is available from the environment. If agent action need to depend on entire percept sequence, the agent will have to remember the percepts. So this is the difference between agent program and agent function. Then there are table driven agents. So there is a table which has the inputs stored in it. So this table driven agent program is invoked for each new percept and returns an action every time. Okay. So it retains the complete percept sequence in the memory. So whatever that is perceived by the agent, it is saved over there. So this function table driven agent has input of percept and it returns an action. Output is action. Input is percept. Persistent means what goes on changing. The percepts a sequence, initially it is empty, later on one by one the entries will be made over here, and a table, that is table of actions indexed by percept sequence. It means that if this was the input, what is the output? If this was the input, what is the output? Likewise, the entries are made in the form of table. Then append percept to the end of percepts. Okay, so when new percept comes, we append it to the end of percepts which are already stored, and action is look up to the percepts comma table. So in the table it will look that if similar input was there or not. If similar input is there, then what was the action that was taken? So action will come from lookup table, and that action will be returned to the actuator. Okay, so this is table based agent. It is instructive to consider why the table-driven approach to agent construction is doomed to failure. Why it is doomed to failure? There is a problem. Problem is if P be the set of possible percepts and T be the lifetime of agent, the total number of percepts it will receive. Here we are just tabulating. Okay, what is the input? What is the output? What is the input? What is the output? That is the table. The lookup table will contain summation t is equal to 1 to t mod of p raised to t entries. Consider the automated taxi. Example of automated taxi, driverless taxi. The visual input from a single camera comes in at the rate of roughly 27 megabytes per second, 30 frames per second, 640 by 480 pixels, which is very small image size. Nowadays, in our mobile phone, we have very good resolution. There is very less resolution, 640 by 480 pixels. Okay. Likewise, if the image is RGB, then 24 bits of color, like 3 planes are there. So 24 bits per pixel. And for this 640 by 480 size, how many frames are there? 30 such frames or 30 such images are coming per second as input. This results into very huge amount of data, and 10 raised to is very big number. These many entries for an hour's driving. Within 1 hour, these many entries. Where will you store such huge table? So even lookup table for chess, a tiny well-behaved fragment of real world, would have at least 10 raised to 150 entries. That is very, what do you say, very simple application. In real life, the applications are complex. The daunting size of these tables, the number of atoms in the observable universe is less than 10 raised to 80. Means that no physical agent in this universe will have the space to store the table. Limitation, big limitation. The designer would not have time to create the table. These many entries. So the designer will not everywhere, and it will not. This is the input. This is how you have to behave. Like the experience. Fourth one, even if the environment is simple enough to yield a feasible table about how to fill the table entries. So many problems. One thing, by common sense, what we do, if we drive a vehicle, say if we drive a bike or car, we don't look at every minute detail continuously. Okay, we focus on few things, we carefully drive the vehicle. Okay, the inputs are coming from so many sensors, our human sensors, but we don't capture every precise thing. For this agent, this is the limitation. It has to capture every precise thing and then record. Okay, human beings can process this much of data, they can take the action, they can drive. But for computers, it is difficult. Then that's why the scientists can till now cannot mimic the human brain. The processes that go on in the human brain that are biochemical processes which are difficult to understand, we just use mathematics to mimic or to replicate the few of the things, but exact replica is not possible yet. And that's why human brain is really powerful. Machines are not. They are powerful in processing the data which is structured, which is repetitive, which has some formula, they can do well. Or the field is still developing, AI field is still developing, where we continuously strive hard to understand the processes and to mimic them with the help of mathematics. Simple reflex agents. The simplest kind of agent is simple reflex agent. These agents select actions on the basis of current percept. Okay, only current input, ignoring the rest of percept history. For example, the vacuum agent whose agent function is tabulated is a simple reflex agent because its decision is based only on the current location and on whether that location contains dirt or not. Function, reflex vacuum agent, location and status, dirt is there or not, which is the location, returns an action. If status is dirty, then returns a. If the location is A, then return right. If location is B, then return left. So very simple thing. Only one input, one set of inputs present percept. Simple reflex behaviors occur even in more complex environments. Imagine yourself as the driver of automated taxi. If the car in front brakes and the brake light come on, and then you should notice this and initiate braking. Okay. So if front car has applied brakes, light is on, brake light is on, then you should also apply the braking. In other words, some processing is done on the visual input to establish the condition we call the car in front is braking. This triggers some established connection in the engine program to the action initiate braking. We call such a connection condition action rule. If car in front is braking, then initiate braking. This condition action rule. Humans also have many such connections, some of which are learned responses as for driving, some of which are innate reflexes such as blinking when someone approaches the eye. Isn't it? If someone suddenly approaches with some object to your eye, what do you do? Blinking, you close the eyes. So there is innate reflex. And some are learned responses or learned reflexes. This is simple reflex agent. Over here, sensors, what the world is like now, then what action should I do now, that will come from condition action rules, and the action is taken. So this simple reflex agent. Next is this function. So percept means current input. Interpret the input of percept, that will give us the state. Then rule match, in the table will match with the state and rules, it will give us the rule, and corresponding action is taken. Then model based reflex agents we are going to study in the next lecture. So today we discussed about what are the different types of definitions of AI. Okay, I'll revise. What are the different types of definitions of AI? Like a logic-based definition, thinking rationally, acting rationally, and thinking humanly. And acting humanly, we already discussed in the last lecture with the help of Turing's test. Okay, and then we discussed what is agent, what is rational agent, what is environment, how the sensors and actuators behave. We discussed the example of vacuum cleaner, which has very sophisticated environment. Then we discussed the concept of performance measure, which is important to gauge the performance of certain agent. Then we discussed the simple reflex agent, and in the next lecture we are going to discuss other types of agents. With this, we will stop here for today. We'll download the attendance list and then you can log out. Any doubt, any query? Okay, then we will stop here. Thank you for attending the lecture. Bye bye.